All right, this is chapter 2 for physics 202. A proton that moves 2 centimeters parallel and in the direction of a uniform electric field of 200 newtons per coulomb. So if this is my electric field, I have this positive charge, this proton. It's going to move in this direction because the force due to the electric field follows the electric field lines for a positive charge. I wonder how much work is done by the field on the proton for part A. Well, work is just force times displacement. Actually, we're going to treat those as scalar quantities. This is my force. My displacement is a vector in this direction at 2 centimeters. And my force is, I can calculate the magnitude of my force based on the electric field. Q times E, that's going to be 1.6 times 10 to the minus 19 coulombs times the electric field, which is 200 newtons per coulomb. Now let's see, that is 3.2 times 10 to the minus 17 newtons. So that's the force that this charge feels, and it acts over a distance of 2 centimeters, so it's 3.2 newtons. Over 2 centimeters, that's going to be 0.02 meters. And that gives me the answer for the work is 6.4 times 10 to the minus 19 joules. That's for part A. That's the work that the field does. What change occurs in the potential energy of the proton? All right, look, this proton is gaining kinetic energy. So we can imagine that it's losing potential energy. And so if we think about it in that way, then the potential energy is going to, the change in potential energy is going to equal to the negative of the work done. That's energy that the object once had as potential, and now it's lost it. All right, it's the negative of the work done, so it's going to be negative 6.4 times 10 to the minus 19 joules. It's just the negative of the work. So it loses that amount of potential energy. The kinetic energy increases, and the potential energy decreases. And now what is the potential difference? Or what potential difference did the charge move through? All right, well, your change in potential is just your energy over your charge. Actually, it's your change in your potential energy over your charge. Potential is just a measure of energy per unit charge. All right, and so that's going to be negative 6.4. It's 10 to the minus 19 joules divided by the charge, which is 1.6 times 10 to the minus 19. So that's what, 4 volts, negative 4 volts. So it moves through a potential difference of negative 4 volts. You might want to think about it more in this way. Instead of looking at these parallel electric field lines, let's think about it in this way. If let's say I have some positive charge here, and I have these field lines that come out from it, and then I can draw my equal potential lines here and here. And these are going to have a potential difference between them of 4 volts. All right, so my charge is going to move from here. My proton is going to move from here. And it's going to move in this direction because it's repelled from that plus Q up to here. All right, move through a potential difference of 4 volts. All right, now I know that in order for it to move there, that it has this field, it acts on it, have this change in potential energy, which is because of this change in the potential. Now, I also know that V is equal to KQ over R. So closer into the charge, I'm going to have a bigger voltage or a bigger potential. So if R goes down, V goes up. So let's say then if this is 10 volts, then out here, this has to be 6 volts. right, because it's lower. And then my change in potential between this point and this point, this is going to be VF, this is going to be VI, 6 minus 10, which is equal to negative 4 volts. All right, so that's where that negative comes from. Then I'm moving from a place of low potential, or excuse me, from a place of high potential to a place of lower potential. We'll see more of that in these problems to come. All right, charged particle is accelerated with a potential difference of 60 volts, has its potential energy decreased by this amount. Calculate the charge on the particle. Is the charge positive or negative? All right, so as I said, my change in potential is equal to the potential energy, the change in the potential energy over Q. And so I can calculate Q then is going to be the potential energy, which is 2.42 times 10 to the minus 17. And actually this is negative because it's decreasing, divided by, divided by delta V, which is going to be 60 volts. This is delta V. It's equal to 60 volts. This is in joules. Joules over volts gives me charge, and that's going to give me 4 times 10 to the minus 19 coulombs. Negative 4 times 10 to the minus 19 coulombs. That's Q. That answers the second part of the question too, that the charge is negative as well. Let's think about this more in conceptual terms. Let's say, again, that I have this electric field. We'll say that I have a positive charge here, some positive charge that's creating an electric field. These are the field lines emanating out from that charge. All right, I have some equal potential lines right there and right there. Those are equal potential lines. We'll say that close in, we'll say that this is 100 volts and that this is 40 volts, and that gives me that potential difference of 60 volts. And now in order to have my my potential energy decrease, I want to think about, all right, well, so in order to have a change in potential of 60 volts, delta V is equal to VF minus VI. All right, so that's going to be 100 minus 40 will give me that positive 60. That means that this is going to be my final position, and this is going to be my initial position. That means that my particle is going to start here and go in this direction in order to have a change of delta V equals plus 60 volts. Now, that particle that's going to move from here to here has to be a negative particle, and it's attracted to the positive particle in the middle. All right, this particle sees an increase in kinetic energy and a decrease in potential energy. All right, so that's where this potential energy decreased by that amount. Oh, but you might say, well, what if instead of being a positive charge, let's say that it was a negative charge that we had, and so our field lines now are the opposite. Right, and then I can draw some equal potential lines. Like that. Then, close in, this is going to be V equal to negative 100, and this is going to be V equal to negative 40. And then, in order to get a delta V of 60, I'm going to have negative 40 minus negative 100. That means that my particle is going to start here, and it's going to move in this direction. In order to do that, guess what? I have to have a negative particle, because it's going to be repelled by that negative Q. And then it's going to move in this direction. It's going to see its kinetic energy increase, because it has this force acting on it, speeding it up, doing work on it, and its potential energy decrease. All right, so let's just sort of that in theoretical terms, but that falls out in the equation for our definition of potential energy and voltage, or excuse me, potential energy and charge, which is here. A change in potential is a change in potential energy per charge. Potential is just potential energy per unit charge. All right, let's move on. Find the electric potential 1 centimeter from a proton. What is the electric potential difference between 2 points that are 1 and 2 centimeters from the proton? All right, so this is my proton. I want to know, these are my electric field lines. I want to know what is the electric potential at 1 centimeter. So what is this equal potential line right here? If this distance is 1 centimeter, and then likewise at 2 centimeters, what is it? All right, well, V at 1 centimeter is just kq over r. So this will be 9 times 10 to the 9th. Q is for a proton, that's 1.6 times 10 to the minus 19, divided by r, which is 0.01 meters. And then I find that potential at 1 centimeter is 1.44 times 10 to the minus 7 volts. And then likewise at 2 centimeters, it's going to be kq over r again. 1.6 times 10 to the minus 9 divided by 0.02 meters. And of course, this is going to be half what it is at V1. 7.2 times 10 to the minus 8 volts. And then if I want to know the difference between points 1 and point 2, I'll say V2 minus V1. Is that what I'm asking for? Well, it's not clear. Let's say I want to know if I move a particle from V1 to V2, what potential does it move through? So I'm going from V1 to V2. All right, this is going to be V final minus V initial. And that's going to be a negative change in potential, negative 7.8. Excuse me. Negative 7.8 times 10 to the minus 8 volts. Have to be very clear about what is your initial and final position when you're calculating potential. All right, and I wasn't there, I'm sorry. All right, find the electric potential taking 0 to infinity at the upper right corner. That is at this point with these charges. All right, so I have, remember, potential is a scalar quantity. So if I want to find the potential at that particular point, I just need to find the potential due to this charge, and this charge. All right, I'll call this Q1, Q2, and Q3. So V is going to equal to V1 plus V2 plus V3. In the course of this, I'm going to need to know what this distance is. But look, this is 3 meters, 4 meters. So this is the square root of 3 squared plus 4 squared, which is 5. Let me write that out. 5 meters. So V1 is going to be K times Q1, which is 6 times 10 to the minus 6, all over R, which is 4 meters. That's this distance. Plus K times Q2, which is 2 times 10 to the minus 6 coulombs, divided by 5 meters, which we found from the Pythagorean theorem, plus K is 4 times 10 to the minus 6 coulombs over 3 meters. V is equal to KQ over R. V is a scalar quantity, so I just add them right up using K equal 9 times 10 to the 9th I get 2.9 times 10 to the 4th volts. Right, now, this was part A. What if, for part B, you let this 2 microcoulomb charge now become negative 2 microcoulombs? Well, it works out exactly the same for part B. All that you change here is that this now becomes a negative value. And if you do that, instead of 2.9 times 10 to the 4, you get 2.2 times 10 to the 4 volts. All I did was make this value negative right here, this 2 times 10 to the minus 6, because it's now a negative. So now instead of adding potential, it's actually taking away potential at that point. This is useful because if you can arrange charges in particular ways, you can create potential fields, which will allow you to manipulate charges in any way that you like. All right. 3 charges situated at corners of rectangles in this figure. How much energy is required to assemble these charges, assuming they come from a very far distance away? All right, so this is the same scenario we had before. First, we just want to take each individual charge and ask ourselves how much work. Remember, work is equal to Q times delta V. How much work is required to bring that charge in? So let's first just imagine we have an empty space, and we bring in our 6 microcoulomb charge. Work for this charge is equal to 6 microcoulombs times delta V. Now delta V for this charge, coming from an infinite distance away to this place where there are no charges, is equal to 0. So it's just equal to 0 joules. Now let's imagine that we bring in our 2 microcoulomb charge. It's at a distance of 3 meters. Work for this is equal to Q delta V. That's going to be 2 microcoulombs times the potential at this point due to the 6 microcoulomb charge. So it's going to be K times 6 microcoulombs over 3 meters. Putting in the proper value for K and converting your units from microcoulombs to coulombs, I get 0.036 joules. Now I bring in my 4 microcoulomb charge over here. Now, this at the position where this charge is located, there is potential due to this charge and this charge. And so you have to include both of those when you're calculating the work. And so the work is 4 times 10 to the minus 6 coulombs times K times 6 microcoulombs over 5 meters. Remember, because this distance was 5 meters. That's right. Plus K times 2 microcoulombs divided by 4 meters. All right, and then that gives us the work to bring in that charge, that 4 microcoulomb charge, which is 0.061. Now to get the total work, I'll call this W3, we'll call this W2, and this W1. To find the total work, it's going to be work 1 plus work 2 plus work 3. They're scalar quantities, so they just add right up. That's 0 plus 0.036 plus 0.061. As you add each successive charge, you have to consider the voltage or the potential that is created by the previous charges that you've added. Right, so that's 0.097 joules. That's the answer. So that's the amount of energy that's contained in this configuration of charges. And if you were to let them go, that's the amount of energy that they would fly away with 0.097 joules, distributed between the charges in some particular way. All right, the electric potential in a region of space is given by this function. If P is at 111 meters, find the potential at P. Okay, well that's pretty easy. The potential is just equal to 2 times x, which is 1, times y, which is 1, minus 3 times z, which is 1, times x, which is 1, plus 5 times y squared. That's 1 squared. So it's 2 minus 3 is negative 1, plus 5 is 4 volts. All right, just plugging in the numbers, the position, into the function for the potential. Now I want to find the electric field. Remember, the electric field we can find from the potential. The electric field is dependent upon the derivative of the potential. In particular, Ex is equal to the negative of the partial derivative of V with respect to X. Remember, when you're taking the partial derivative, you just look at the term and you imagine that everything but X in this case is a constant. All right, so the integral, the derivative of 2xy with respect to x is just going to be 2y. The derivative of 3zx is just going to be minus 3z. Minus because I had a negative sign here. And then 5y squared doesn't have an x on it at all, so we just treat that as a constant, and the derivative of any constant, since it doesn't change, the derivative tells how much something changes, and the derivative of a constant then is 0. So that's it. Ey in a similar way. Don't forget the negative. It is 2x minus 0 plus 10y. The middle term right here, the derivative of it with respect to y is 0 because there is no y. So you just treat it like a constant. This was Ey. And then Ez is negative del V del Z, which is negative, let's see, 3x. All right, and then we can put in our coordinates, which are 1, 1, 1. So let's see, this is negative 2 minus 3, negative 1, negative 12, and negative 3 for E, X, Y, and Z. And so in vector notation then, my electric field is going to be 1I minus 12J minus 3K. All right, and then I can take that and do all sorts of things with it, like I could calculate forces and accelerations like we've been doing. It's very useful if you can find the electric field from the position, from the potential function, just the partial derivative. All right, a 60 times 10 to the minus 15 farad capacitor has this plate area. Determine the plate separation. And we're assuming a parallel plate configuration like this, which are most capacitors. This is the distance d. These plates have an area A, and then C is equal to epsilon naught, that's permeativity of free space, times A over D. Epsilon naught is equal to 8.85 times 10 to the minus 12. It's in farads per meter. You might see the units for that in various ways. It comes into the Coulomb's constant, K. K is actually equal to 1 over 4 pi epsilon naught. They're related. All right, so this is just basically plugging in. I have my capacitance 60 times 10 to the minus 15 farads. Times A, which is given, over D. If I solve this for D, I find that D is equal to 3.1 times 10 to the minus 9. All right, and then it tells us that an atom, the diameter of an atom is about an angstrom, that's 10 to the minus 10 meters. I want to know how many atoms will fit across between the parallel plates of the capacitor. So how many, if they're lined up side by side, atoms will fit across the plates of a capacitor, in between the plates of a capacitor. And so to get that, we just say 3.1 times 10 to the minus 9 meters over an angstrom, 10 to the minus 10 meters. Of course, that's 31. So I can fit 31 atoms across a typical capacitor. They can get pretty close together. Usually, in a capacitor, you're actually going to have a dielectric in between them. Dielectric, we talked about this in class, but we don't see it in the homework. So let me just go ahead and show you this here. The dielectric changes our capacitance formula. There is a certain dielectric constant. It's called kappa, that is greater than 1 for a particular material. And when you put a dielectric in, it increases the capacitance of that capacitor. It's kappa epsilon naught A over D. All right, and for a vacuum, kappa is equal to 1. So this is considered to be for a vacuum where kappa equals 1. All right. Series circuit consists of these capacitors, a 400 volt battery, find the charge on each of the capacitors. Alright, so I have a 400 volt battery and 2 capacitors in series. First of all, let's just remember our rules for capacitors in series. Alright, first of all, define the equivalent capacitance is 1 over the inverse like that. Capacitors in series have the same charge, and capacitors in series, their voltages add up to give the total voltage. Alright, so I'll call this one is 0.050 microfarads. This is 0.1 microfarads, and I have 400 volts. I want to know what is the charge on each of these capacitors. If they're in series, they have the same charge. That's one of my basic rules for capacitors in series. All right, so I want to find the equivalent capacitance of these two. That is, what single capacitor could I replace them by? And I can find that. C equivalent is equal to 1 over 0.05 plus 1 over 0.1. And that's equal to 0.033. All right, so now I can also find the charge on this equivalent capacitance. Q is equal to CV. That's going to be 0.033 microfarads times V, which is 400. Which gives me 0.033 times 400. 13.2 microcoulombs. So that's the charge on Q1 and on C1 and C2. They both have 13.2 microcoulombs. By the way, if I wanted to figure out now what is the voltage, like let's solve this C1 and C2, this problem doesn't ask this, but if I did want to know V1, for example, I would say V1 is Q1 over C1. That's going to be 13.2 over C1, which was 0.05. I get 264. And then likewise, I could do V2 is Q2 over C2. It's going to be 13.2 over 0.1, which is 132 volts. All right. If you add these together, you get some rounding errors, but if you add 264 and 132, they should add up to give you 400, and they do. Within rounding, there's some rounding errors, give you 400 volts. We'll see that in problems to come. All right, that's in series. That's a little more difficult. When you do them in parallel, it's a little easier. So let me show you. 400 volt battery, capacitors in parallel. I can tell when capacitors are in parallel because if I follow along in the circuit and I come to a break in the circuit, that signifies the beginning of a parallel branch. Now these are obvious here that they're parallel. I hope they should be obvious, but we'll come to somewhere it won't be so obvious. And then where the circuit comes back together, if I follow it through, you see it comes back together here, that's the end of the parallel branch. And then it goes back along with the circuit. Okay, so now I have C1 and C2. Let's see, is 0.05 and 0.1 microfarads. And I want to know the charge on each. This is 400 volts here. Let's go over our rules for capacitors in parallel. First of all, the equivalent capacitance is C1 plus C2 plus however many capacitors there are. Capacitors in parallel have the same voltage and that's all you really need to know for now, I think. Yeah, that's all that's really relevant here. They have the same voltage. So these two capacitors have the same voltage, so they both have 400 volts. They both have 400 volts, so I can find Q1 is C1 over V1. It's going to be 0.05 over 400. And likewise, Q2 is C2 over V2. That's going to be 0.1 over 400. .05 over 400. You get 1.25 times 10 to the minus 4 in microcoulombs. And then, I'm sorry, no, I've done this incorrectly. That's not right. Sorry about that. This is C1 V1, C2 V2. All right, so C1 is 0.05 times 400. That's 20. And then 0.1 times 400 is equal to 40 microcoulombs. Right, the circuits get a bit more complicated, like this one, for example. In this figure, I have a 10-volt battery, and it's hooked up to these capacitors. C1 is 2 microfarads. I'm going to leave the units off. 2 microfarads, just to make it easier. C2 will be 4 microfarads. C3 is 2 microfarads. C4 is 12 microfarads. C5 is 8 microfarads. And C6 is 8 microfarads. All right, if you have a problem like this on the test, I'll put the capacitances on the circuit. It makes it a little easier. Anyway, so this is the circuit that I have. The first thing you want to do is just sort of assess the circuit and figure out what are the parallel branches and what are the series branches. You know, so you could do like you did before. Imagine my electrons flowing through here. All right, look, this is the beginning of a parallel branch. All right, when it breaks up from here, it goes here. This is one side of that parallel branch. Oh, and then it comes back to another junction right here. And then the other side of the parallel branch comes here, splits again, that comes back, and then it comes back and meets back up here where it left off. All right, so I can redraw this in this way. And the best way to sort of get this is just to practice with different circuits. So you have a couple here in the homework, you have some in the textbook, and you have a bunch in old exams. So best way to do these is just to practice. All right, that is C1, C2, and C3. That's my 2, my 4, and my 2 microfarad capacitors. They're all in parallel with one another. And then they all come back together right here. And then you have the start of a new parallel branch. You have this capacitor, which is 12 microfarads. And then over here you have 2 capacitors, which are in series. This is 8 and 8 microfarads. So this is that circuit. It's the same circuit, it's just sort of redrawn. But often in circuit diagrams, they're not drawn in the way that we would normally draw them in our class. So on the test, you'll see stuff that's laid out more like this. And in fact, a real circuit diagram can be quite more complex than this. So the first thing you need to do is just be able to look at the circuit diagram and be able to redraw it into more standard way so that you can separate the parallel and series components. Now it's a matter just to we want to find the equivalent capacitance. And I always find it helpful to draw each individual step as I go along. And you might, as you get better at this, you might be able to leave out some of the steps, but let's just draw each individual step. I want to look for the smallest parallel and series components. I see that these 3 are all in parallel. And likewise, I see that these 2 are in series. So I'm going to combine each of those and draw a new circuit. The 2, 4, and 2, to find that, it's going to be 2 plus 4 plus 2 is equal to 8. So this is going to be 8 microfarads. This is my 12. I'm just going to leave it there for now. And then here, I have the 2 8s. That's going to be 1 over 8 plus 1 over 8. It's equal to 4, right? Yeah, 4 microfarads. And this was 10 volts. Now I can combine these 2. 12 plus 4 is 16. I have an 8. Now in a 16 that are obviously in series. Combine those 2. 1 over 8 plus 1 over 16. 16 over 3, which is 5.3 microfarads. So that is my equivalent capacitance, 5.3 microfarads. I can replace all of those capacitors with a 5.3 microfarad capacitor. Now, I want to work backwards. This is 10 volts. What is the charge on this capacitor? Q is equal to CV, so it's equal to 53 microcoulombs. 53 microcoulombs. That means that I'm going to have 53 microcoulombs on this capacitor and 53 microcoulombs on this capacitor. Now let's go ahead and, before I move any further, let's just write a little table up here. I want to, with all the information that I want to know. I want to know let's see, I'm going to just draw a little table. I have 6. 1, 2, 3, 4, 5, 6. This will be my charge, and this will be my voltage for capacitor 1, 2, 3, 4, 5, 6. If you look back at old tests, I often have a little table like this that I just want you to fill in with all the charges and the voltages for each capacitor. And then when you get the first few filled in, they really fall in quickly. Let me show you. All right, so let's go back to where we were. We had 53 microcoulombs on both of these capacitors. All right. This was 16 microfarads, 8 microfarads. All right, now I can find the voltage for each of these capacitors. Remember, voltage, Q is equal to CV, so voltage is equal to Q over C. Voltage is equal to Q over C. So here on this top capacitor, I get 53 over 8. Which is 6.625 volts. So it's 10 volts. Here, I can either say 53 over 16, or I can say 10 minus 6.625 volts. Because I know that the voltage of this capacitor and the voltage of this capacitor must add up to equal 10 volts. So this has 3.375 volts. Now the two methods will give you slightly different answers because of rounding errors. Okay, but I'm just going to go with what I have here. 6.625 and 3.375. Now, when I take this information, this 3.375 volts, that's going to be the voltage on each of these capacitors because they're in parallel. All right, and this one is also going to have 6.625 volts. Now I can start filling in some of my stuff because see this capacitor right here, that is this capacitor. So I have 3.375 volts for C4. And then I can calculate what Q is. Q is just equal to C times V. And so that's going to be 40.5 microcoulombs. That's just saying 12 times 3.375. Okay, so I started filling them in. Now, up here, I have 6.625 volts, as I found. But this is the equivalent for this 2, this 4, and this 2 microfarad capacitor. Since those are all in parallel, that's going to be my voltages for C1, C2, and C3. So this is going to be 6.625, 6.625, and 6.625. They all share the same voltage. All right. In a similar way, I can just multiply the capacitance times the voltage, as I did for C4, and find the charge. So it's going to be 13.25, 26.5, and 13.25. Those are all in microcoulombs. Now, the only thing I'm missing is this C5 and C6. Now, I already know that the voltage across here is this 3.375. So I know each of these are going to have 3.375 divided by 2. You see, because if I have 3.375 volts across this capacitor, I also have 3.375 volts across these two capacitors. Since they're identical, they split that voltage equally. So 3.375 volts divided by 2, which is 1.69. We'll call it 1.69 volts. All right, and then you can calculate the charge. I get 13.5. You might get slightly different numbers. I actually carried more significant figures than I'm showing here. All right, so your values might be a little bit different from that. Okay, so we'll do these in class, and I know it might seem a little overwhelming because there's a lot of little things that seem to happen, but you really just have these basic rules, and you just have to learn to apply them. It's sort of like a puzzle, like a Sudoku puzzle or something, but you just want to fit in all these little different rules and figure out what is the charge and velocity. Let's do another one. Really got to practice these. All right, so this is another capacitor. I want to find the equivalent capacitance and the charge and potential across each capacitor. let's do it like I did before. I'll make a little table. So you have 5, 1, 2, 3, 4, 5. I'll say this is charge. This is voltage. All right. I want to find the equivalent capacitance first. First, I actually want to draw a circuit that is the same as these. Come along through here. Actually, usually we go off the positive side of the battery, so let's go this way. Okay, I come to a capacitor. It's in series with the battery, and boom, I hit a junction. All right. Now this junction comes here. I hit another junction, but without going through any capacitors. That doesn't really matter. So I come to my first capacitor, my capacitor there. Those three capacitors are all parts of three separate parallel branches. Three separate parallel branches. Now these come back together at this point. Go through this capacitor and then through another capacitor. So these two capacitors are in series. And then it comes back here. Now, if I draw this, this is my 20. I have a 2, 3, and a 10. Right. Then I have another 10. And it all comes back. That circuit is the same as this circuit. Those are identical circuits. 100 volts here. All right, I want to combine these two. 1 over 10 plus 1 over 10 is equal to 5. Again, you might be able to simplify some of these steps, make them quicker for you. Then I get a 2, 3, and a 5. I have a 20. Combine that 2, 3, and a 5 gives me 10. And then combine this 10 and 20. 1 over 10 plus 1 over 20. Let's see, that's what, 20 over 3, which is 6.67. That's my equivalent capacitance. Draw it like this. I can find the charge on that capacitor. C times V, that's 6.67 microfarads times 100 volts, which is the voltage across this capacitor, 667 microcoulombs. All right, that's my equivalent capacitance, my equivalent charge. Capacitors in series have the same charge. So both of these capacitors have 667 microcoulombs. All right, but look, that's one of my answers because this 20 microfarad capacitor right here is C5. So how much was it? 667. And then I can go ahead and find the force, or excuse me, the voltage, excuse me. The voltage there is going to be 33.4. So this has a voltage equal to 33.4. I can also find the voltage up here. It's going to be Q over C. That's 667 over 10, which is 66.7 volts. I could have done this in two different ways. I chose this way, the charge over the capacitance, but I could have also said 100 minus 33.4, because the sum of the voltage across this capacitor and this capacitor have to equal 100 volts. Right, and they're slightly different, right? I would have gotten 66.6, but it's just because of rounding that they're slightly different. Okay, so 66.7 is the voltage across that capacitor, which means that I have 66.7 volts across these three capacitors, the 2, the 3, and the 5. Now the 2 and the 3 microfarad capacitors are C1 and C2. So I'm going to go ahead and put in 66.7 for these voltages. And then I'm going to calculate the charges. I get 133 and 200. And then our last step is pretty easy. I have these two 10 microfarad capacitors, but I know that the voltage across the two of these capacitors has to be the same as the voltage across these two capacitors, because the capacitors in parallel have the same voltage. And that was what? 66.7. So these two guys both have 66.7 divided by 2, which is what? 33.4. All right, and then I calculate the charges. I get 334 on each of them. (334 microcoulombs). So that's another good example of a capacitor circuit. You should be able to do this. You'll probably see it on the exam and maybe even on the final. All right. Express the potential due to this charge bar at P in terms of L, D, and lambda. This is similar to what we did with the fields, though with electric potential it's a ton easier because potential is a scalar quantity and fields are vector quantities. It's just a lot easier to deal with scalar quantities. I want to know the potential at this point due to this bar. I'm going to break this bar up into little differential elements. They're going to be a length dx, and they're going to be a distance x from the end of the bar. So you can imagine I'm going to integrate over x from 0 to L, right? I'm going to call this distance right here r, and the potential due to that little differential element is going to be k dq over r. K dq over r, where dq is the charge of that differential element. dq is equal to lambda dx. Remember, lambda is the charge density, the line charge density in this case. It's measured in coulombs per meter. So how much charge per unit length is there? Further, I can say that r in terms of d and x by the Pythagorean theorem is d squared plus x squared. Make those substitutions and integrate. I'll go ahead and put integrals here. V is equal to integral of k lambda dx over the square root d squared plus x squared. All right. If you look in Shams, you can probably do this by substitution, but I just looked in the integration tables. The integral of du over u squared plus a squared root is equal to the natural log of u plus the square root of u squared plus a squared. All right, so I'm going to follow that form and do this integral, letting, let's see, what did I let this, u is equal to x, d is equal to a. All right, so let u equal x, d equal a for this form. And then my integral works out like this. I get v is equal to k lambda, natural log, the k lambda just come out of the integral, natural log of x plus square root of d squared plus x squared from our limits of integration from x equals 0 to x equal L. And then my voltage at that point is k lambda natural log of L plus d squared plus L squared root. And that's the answer.